Okay, so what I wanted to do was kind of backtrack, and I mentioned last week that I didn't want to talk about orbital notation with all the arrows up and down because it's very tedious, but I do want to kind of like explain why we use that notation first, because it kind of includes all three rules. If just to review from last week, we have the Aufbau principle, which describes which order to fill the orbitals from lowest energy on up. And then we have the Pauli exclusion principle, which says that, and I actually remember it now, we'll see how long that sticks. But the Pauli exclusion principle, which states that no two electrons can have the same four quantum numbers. So that's why we give the fourth quantum number of spin of +1/2 -1/2, and how that translates to orbital notation is one arrow up and one arrow down in each orbital. And then we get to Hund's rule, which states that when you have sublevels that have multiple orbitals, that applies to P, D, and F. You have to put single electrons in each orbital first before you start to pair them up. Now, in order to kind of reinforce all three of those rules, that's what we use orbital notation for. So I thought I would do some examples of that, and then it also gives me an opportunity to address some of the exceptions that exist in the periodic table and why those exceptions exist. So I'm going to go ahead. I'll start with, let's do argon. And orbital notation means that we're going to draw a line with the orbital identification underneath it, which is the principal energy level followed by the letter of the shape of the orbital. So the first one we fill, of course, is for period 1, that's energy level 1, and hydrogen and helium both belong to the S block, which is these two. So the first orbital we fill is 1s, and Pauli says we have to have the two electrons that are in the 1s orbital have opposite spins. So we draw one arrow up and one arrow down. You might ask, why do my arrows have only half of a point on them? Is because we're putting them next to each other. If you want to do like full arrows, that's fine too. So after 1s is full, so we filled, I'm doing argon, so this is our end point. We filled the first two electrons for 1s. So the next orbital to be filled according to Aufbau, but like I said, following the periodic table is all you need. After helium, we get to lithium, which is in period 2. So we draw another line and we're in level 2. And the first block that we fill is the S block, because remember, groups 1 and 2 are the S blocks. We fill these two in next. So I do one arrow up, one arrow down. So I filled those two. The next one that I have to fill is this. This is the P block, and it's still in level 2. But remember, P has 3 orbitals. So I need to do, oops, sorry, I forgot the S there. My bad. The next one to fill has 3. And in the middle, I'm just going to do 2p. So those 3 lines represent 2p. And according to Hunt, I have to do up, 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 because that has lower energy than pairing them up. And then down, down, down. So these are full. After 2p, I move down to level 3 and the S block. So the next one I fill is 3s for sodium and magnesium, one up, one down. And then finally, to get to argon, I've got 3p, up, 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 down, down, down. Now, this is why argon is a noble gas, because you see the very outer orbital that's available is 3p. Now, it's not just 3p, because when we talk about, I haven't mentioned it yet, but it's a good time to mention it anyway, valence electrons. Have you ever heard of that before? Valence electrons. Valence electrons are the electrons that are in the very most outer level. When we talk about valence electrons, we are referring to the electrons that are in the highest energy level. And here's where it's important to pay attention to detail, because although these 6 electrons might be in the last orbital that you fill, the 3p electrons and the 3s electrons are both in level 3. So they're all going to be in the same energy level. So for argon, all 8 of these electrons are considered valence electrons because they're all in level 3. If we go back to the very simplified structure of an atom, just to demonstrate this point, here's the nucleus, here's level 1. If you look at level 1, it can hold a maximum of 2 electrons. So we put 2 electrons here. Level 2 can hold a maximum of 8 electrons. So I go level 2. Oops, let me try that again. Level 2. Oh, my drawing skills are not strong. So then I've got 8. 1, 2, 3, 4, 5, 6, 7, 8. This corresponds to how many elements are in that level. All right, there's 8 elements. And then we've got level 3. Let's just pretend like that's a proper circle. And again, I've got 8. I've got 1, 2, 3, 4, 5, 6, 7, 8. That's the maximum number of electrons that can be held in that level. And this is what makes argon a noble gas, because it has a full electron configuration. There's no empty spots here at all, not even for 3s either. That's why it's considered a noble gas. Oh, whoops. I didn't start on slide number 1. Okay. Okay. Did I want to talk about anything else for that? Did I go back here? Okay. Right. So the other thing is, so if the electrons that are in 3s and 3p, those are considered valence electrons. All of these other electrons that are on the inside, so that would be these levels here, those are called inner shell electrons, because they're on the inside. So in general, when we're not talking about a noble gas, the valence electrons are the electrons that are available to participate in bonding. And the inner shell electrons belong to this atom specifically. So they're not going to be shared or transferred at all. So that's just some terminology, what we use. But it's important to remember that it's the highest energy level. So that would include 3s and 3p, because they're both in level 3. Okay, let me go back to. Okay, so now I'm going to get into some of the exceptions and show you why they are exceptions to Aufbau. So I'm going to look at chromium. Okay, I'm going to do the same thing with orbital notation, because orbital notation is the only one that shows you exactly why chromium is an exception to Aufbau, why it doesn't follow the rule that we have set. So again, starting off with 1s, and then we fill 2s up, down, then we get to 2p, which is 3 orbitals, up, 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 down, down, down. I got 3s, up, down, 3p, up, 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 down, down, down. Okay, that gets me to argon. And then I've got 4s. Gotta be careful with my space here. Right, after 4s, we're at calcium right now. Remembering once you get into the D block, which is groups 3 to 12, that's the D block. This is N-1. And the D block has 5 orbitals. So I've got 1, 2, 3, 4, 5 lines. And because it's n minus 1, we go down to 3d. Okay. Now, you would expect that 3d, because chromium is number 1, 2, 3, 4. 1, 2, 3, and 4. You would expect it to have this configuration. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. But it is not, in fact, the correct notation, because it turns out, and you wouldn't know this other than the fact that we've done by experiment, that chromium has a lower energy state if one of the 4s electrons is removed and used to fill the 5th 3d orbital. It turns out that having this configuration, so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. It turns out that this configuration is a lower energy profile for chromium than if you have a full 4s2 and a 3d4, because you like the difference in energies between 4s and 3d is very small. And so it ends up being more stable if you just take one of the electrons out of 4s and use it to fill that last spot in the last 3d orbital. So it's not the end of the world, because it turns out that all of the elements in this same group follow the same exception, because they're all in group 6. They're all going to have that last orbital notation of n minus 1 d4. So whether it's 3d, 4d, oh, I got to go back and uncover. In molybdenum, in that example, it's going to be 4d, and for tungsten, 5d, and for seborgium, it'll be 6d, but it's the same profile because they're all in group 6. So they have the same number of electrons in that outer d orbital. They're all going to follow the same pattern. So when you get to group 6, it's important to remember that you remove an electron from the s orbital and you put it to fill in that last d orbital. The other group of exceptions is group 11. And I'll show you why. It's pretty much the same kind of thing. So I'm going to do copper. So again, we'll do 1s, 2, 2s, 2. Remember to make my line so long. 2p6, 3s, 2, 3p6, 4s, 2, and then I get to 3d, 1, 2, 3, 4, 5. Now, how many electrons do I have left? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a similar problem that we did with chromium, only the first 4d orbitals are now paired and full, but the last one has a lone electron. So it's going to follow the same kind of exceptional rule where you take the electron out of 4s and you use it to fill in the last orbital for 3d. So this configuration is going to end up with 4s1, 3d10, because this has a lower energy profile than 4s2, 3d9. And just like group 6, all of group 11 is going to follow the same exception. So this is why orbital notation is an advantage to look at, so that you can understand, like looking at it physically, why it makes sense, because you're filling out that 5th orbital to match the other 4 orbitals. which brings the energy of the atom down, because again, in the universe, just as like a natural, the natural tendency of the way the universe works is to go towards the lowest energy possible, because low energy means more stable. Okay, so are there any questions about orbital notation? Because I just wanted to show you why we use that, and then use orbital notation to explain why those two groups are exceptions. Okay, then I am going to do, let's see, I'll do 2 more examples using just regular notation and or what's called ground state notation. And then I'm going to show you noble gas notation, which is an abbreviation. So let me go ahead and pick iridium. Iridium, by the way, just as a side note, a little factoid about iridium. Iridium is the element which showed us why the meteor impact hypothesis is the currently running hypothesis for the extinction of the dinosaurs. Because when they examined, when we look at fossils, right, we do excavation in the ground. And the way that it works is basically, if here's your ground, newer fossils are going to be towards the top and older fossils are going to be at the bottom, right? Because you're going back in time as you dig down. And it turns out that there was like this kind of this depth. There we go. That's the word I'm looking for. This depth at which underneath you had, I'm going to try to draw a dinosaur. Oh dear. Oh, that's got a tail. All right. That's a dinosaur. Just trust me. That's a dinosaur. Actually, wait. Whatever, you get it. And then here's his tiny little arms. There we go. That's a T-Rex. Okay, so underneath this level, if you haven't figured it out by now, I really just cannot draw at all. So underneath this level, you had dinosaur fossils, but above this level, you had no dinosaur fossils. And it turned out when they chemically analyzed the elements right around here, they found very high concentrations of iridium, which is not normally found on Earth, but it is quite often found in things like meteors, meteorites, and comets and things like that. So that was a huge key piece of evidence to help support the meteor impact hypothesis. There's a couple of different running hypotheses at the moment, whether it was one big meteor or several smaller but quite large meteors that all kind of hit the Earth and then like spewed all the dust and blocked out the sun. And so then, of course, like temperatures plummet and plants die. And because dinosaurs were all reptiles, they are what are called conformers or cold-blooded. So with dropping temperatures, they would die. Anyway, we can be thankful for the extinction of the dinosaurs, because without them dying out, mammals would not have been able to evolve, because they call, was it like the Jurassic period and the Cretaceous period, they call that the golden age of reptiles or something like that, because reptiles were like the dominant organism on Earth. And the extent of mammalian evolution at that point was like rats. So there was no more complicated mammal than like basically a rat, like a small rodent. And so once the dinosaurs went extinct, then mammals were able to come out of the ground and evolve into many, many different life forms. And now we're the dominant life form. Anywho, iridium. Oops. So we're going to start off at the beginning, 1s2, 2s2, 2p6. And normally I would be able to point to the periodic table as I'm doing this to track where we're going. 3s2, I'll just do it like that. 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Don't forget, at barium, we have to go down. for F14. Then we go back up to, this is period 6, but this is the D block. So I'm in 5D. And then 1, 2, 3, 4, 5, 6, 7, 5D7. Ta-da! That's iridium. Now, if I don't want to go through all of that, I can use what's called noble gas notation or noble gas abbreviation. What that means is you basically go from the nearest previous noble gas. So I'm going to use iridium again. You go back to the nearest previous noble gas. So I'm going to go, okay, back to the noble gas, whoop, and got to go to 5 xenon. And instead of doing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, blah, 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 blah. Instead of going through all of that, I'm going to say, okay, square bracket, xe. So everything that comes before xenon is abbreviated with this symbol. And then I'm just going to specify the configuration that comes after xe. So then I do what comes next, 6s2, don't forget, come down here, 4f14, go through here, back up, and 5d7. That is called noble gas notation. It is important to remember, let me double check, you cannot use noble gas notation as an abbreviation for that noble gas. So if I ask you noble gas notation for xenon, you cannot use xenon. I would hope that would be kind of self-explanatory, because like when you define a word, you can't use the word in definition, right? Hopefully you learned that in English class.